Hello and welcome back to 4.4 lesson 4.4. All right, we're gonna have to deal a little bit with fractions. We need to talk about valid and invalid strategies for changing the form of fractions. Students have suggested that the following equations are true. Examine each problem to determine if the two fractions are equivalent. You can verify your prediction numerically by calculating decimal equivalents of the fractions on each side of the equation. Okay, so are these the same? What have they done here? They have pulled this 6 apart to 2 times 6 and then quote-unquote canceled. No, because order of operations says we got to do this plus sign first. This should be 2 plus 5 is 7. Seven sixths does not equal 5/3. What they were trying to do is if it said 2 times 5 divided by 6 equals 5/3. Now, multiplication is much more flexible because you can rewrite 6 as 2 times 3, and then this is a 1. If you multiply by 2 on the top, divide by on the bottom, and then we get 5/3. Dink. Or, if it was 2 times 5, which is not, it's 2 plus 5, but if it was 2 times 5 over 6, you could also just do the multiplication and get 10 sixths, which is equal to 5/3. 10 sixths is equal to 5/3. You have twice as many pieces, but twice as many parts. So it all lines up. What about this strategy? Oh, this time, instead of canceling entirely, they've cut it in half, and they cut this in half. No, again, you have to do the whole top has to be reduced in half. 7 sixths versus 6/3. That's not, this is barely bigger than 1, this is 2. And lastly, is this allowed? Okay, yes, this is allowed, and this is what happened here. This is 2 plus 5, then times a sixth. Divide by 6 times a sixth is the same thing. Order of operations, this happens first. Order of operations, fraction bar creates a group. Groups first. Here's our group. Happens first. But then we can distribute. You can actually distribute in this mode as well, but I wanted to rewrite it like this so it looks like distribution. A sixth times 2 is 2 sixths. A sixth times 5 is 5 sixths. That's the plus sign. 2 sixths is 1/3. 5 sixths is 5 sixths. And look, that's what they wrote here. That's how they got there. They pulled it apart. I call this pulling a fraction apart. Because remember that 1/4 plus 3/4 plus 5/4 plus 2/4. You just, they're all fourths, so let's just count up how many fourths we have. We have 4, 9, 11. When you're adding up the top, the denominator doesn't change. If you just add. So if you had A plus B plus C plus D all divided by 4, you could rewrite it as A over 4 plus B over 4 plus C over 4 plus D over 4. That's what I call pulling a fraction apart. Okay. Let's get on to the triangles. Instructions on 2 different pages. Our learning focus. Prove that a line drawn parallel to one side of a triangle intersects the other 2 sides and divides the other 2 sides proportionally. Okay, parallel. A line drawn parallel to one side will intersect the other 2 sides and divide those sides proportionally. Yes, we're learning about more proportions. Draw 2 intersecting transversals on a sheet of paper as in the following diagram. Label the point of intersection of the transversals A. Label the other ones B and C, D and E. Well, we're just going to use this. They've drawn it for us. Let's just go with it. B, C, D, E. said. What convinces you that the two triangles formed by the transversals and horizontal lines are similar? Note, we can assume that horizontal lines on a sheet of line are parallel. Oh, okay, well, if they're parallel, then if these lines are parallel, and this line is on the line of the sheet of paper, this angle and this angle are the same, and this angle is the same to itself. So now we have angle-angle similarity. So these are similar. Corresponding angles theorem states that those are the same. And I guess the reflexive property. I don't even know if that needs to be the reflexive property. It's just that angle A is angle A. Huh? Maybe it is. Usually we use reflexive property for segments, not angles. Write some proportionality statements about the sides of the triangles you have drawn, and then verify the proportionality statements by measuring the sides of the triangles. 8. Here we go. Well, what do we think? We think that probably AC compared to AE must be the same proportion of AB compared to its corresponding side of the bigger triangle, which overlaps it, of course, which is confusing. But so the small side of the small triangle, or this side of the small triangle, versus its bigger version of the big triangle, which mostly overlaps itself, but is a different side. Now let's measure them in millimeters. 4 and 5. Okay, cool. Yeah. I can't remember if I was on the screen when I wrote this down. Oh well, hopefully you followed along. Mr. Abden can't be perfect. This is not how it is. Oh boy. 3.5? 4.25? You're killing me. Hope those are at least close. I'm going to say this is closer to 4.3 because 3.5 divided by 4.3 is 0.81, but then it should be equal to this fraction, 4/5. 0.8. Oops, clear that again. 4 divided by 5. 0.8. So there, I'm going to chalk that up to measuring error, and we're going to say true. These proportionalities are true. Select a third horizontal line segment to form a third triangle that is similar to the other two. Oh man. I should have measured first and chosen my line second. Oh, let's just call it 2.5. Great. 2.5 versus 5. 2 versus 4. I mean, it's slightly less than 2 and slightly less than 4, but J and K. Let's do it up here. AK divided by AE is the same as AJ divided by AD. And we measured AK to be 2.5 centimeters, and AE was 5, and AJ was 2, a little bit less than 2, and AD was 4. And those are both equal to half. The proportionality holds. Because these are all similar. Yay, yay, yay. Now it's going to get interesting. Because Tristan, in 5th period, has written this proportion for problem 3 based on the diagram. BD divided by AB equals CE over AC. Notice that this is not a side of the triangle, nor is this. He is making proportions based on little pieces of the big triangle. But are those pieces proportional? What is he comparing them to? BD over AB. So this little bit over versus this side. is this leftover bit compared to this side the same as this leftover bit compared to this side? Is Tristan right? Oh man, they've added extra ones. Why did they do that? All right, so once again, his statement BD over AB is saying this leftover bit compared to this side, that comparison, I don't know, what is it, a sixth, a fifth? Well, this will also be a fifth, a sixth, whatever it is. This little leftover bit compared to this side. Could this be true? All right, let's measure. First, the little bitty. Ooh, let's call that 7 millimeters versus 35 millimeters. Aha, I knew it was a fifth. Can't trick me twice. 8? No. 9 millimeters. And then, so this should be 45 millimeters. No. It's only 42. So this, what's wrong here? Let's see, where did I go wrong? Double check my measurements. I mean, 42 is pretty close to 45, but I thought this would be spot on. I thought we were going to hit this one out the park. Baseball reference. That does look like... Yeah, I'm accepting all of those. This must not be... This... Ugh, so frustrating. It's just a little bit less than 9. All right. Let's see if those are equal to a fifth. Okay, 0.2, that's 1/5. 2/10, 1/5. And the other one, more complicated, 8.5. Yes! Haha! That is exactly a fifth. So, Tristan's proportions are true. The proportion statement is true. But why? Is it always true? Does it always work? Took the same idea from your own diagram? No. Based on your examples, you think Tristan or Tia is correct? Tristan. Okay. Tia is still not convinced. Since Tristan has based his work on a single diagram, she decides to start with a proportionality she knows is true, that AD over AB is equal to AE over AC. How do we know? How do we know is this true? All right, let's check it out. AE. Nope, I screwed up. AD over AB. Oh yeah, this is a similar triangle proportion. This is what it says below. This is what T is starting with. Equals AE divided by AC. So that's true. But then Tia realizes that she can rewrite AD as AB plus BD and the other one as AC plus CE. Why is that allowed? Well, look at AD up here. It is literally the distance AB plus BD. And the other side, A to E, is literally AC plus CE. So yeah, AB plus BD, AC plus CE. So this is this is this, just rewritten using segment addition. And now can we algebraically prove that Tristan is correct? Yes, we can. Here's why. We pull apart this fraction. So remember that whole part at the beginning where I was talking about pulling apart fractions? Because look, this is the same denominator. So if you're just adding the tops of fractions, then we could just write it like this. AB over AB plus BD over AB equals AC over AC. This pulling this one apart now. That fraction and then the other one. Plus CE over AC. Okay, so let's just double check. Can we add this back together? Yeah, the denominators match, so it would be AB plus BD on top. And then, oh, that's what we have, AB plus BD on top, and then AB is the denominator. Okay, yay, this is why they make you add fractions together in 6th grade, so you can do geometry later. Perfect. Okay, but what is AB divided by AB? What is anything divided by itself? What is 7 divided by 7? What is 10 divided by 10? What is x divided by x? 1. What is AC divided by itself? 1 AC divided by 1 amount of AC is 1. There's 1 there. 1 group of AC inside of an AC. And this. But now we can do the algebra. And we're left with just, let me think, BD over AB. Could this be Tristan's statement that we've already verified by measuring? These are both equal to a fifth? Yes, these comparisons, these proportionals are true. BD divided by AB is equal to CE over AC. Let's just double check that's what Tristan said at the top. Ding ding, BD over AB equals CE over AC. So this idea that you don't have to have whole sides, but you can grab little bitties of bits between parallel lines, as long as the parallel lines are parallel to the side of the triangle, it will always divide up the sides into proportional bits. So this will be proportional to this, and not only that, but this will be proportional to that, and this will be proportional to that. Yeah, this little thing will be proportional to that, as this is to that. I mean, you always need two comparisons to be proportional. So let me just write that last one. BD, that chunk, compared to FD equals CE compared to EG. Nice. And that is known as the side splitter theorem. Actually, I don't think very many people call it the side splitter theorem. They call it the basic proportionality theorem, or triangle proportionality, or Thales theorem. Alright, that's enough learning for one day.